Nice to show everybody. This is Ben. He's talking. That's Ben, and he provided the food. And I'm Ben, and I work here. So it's a Ben party. I've been here in 5 minutes.
Yeah. Okay, let's take it away. So, yeah. So I guess I should just say I always put my slides on my website. So sometimes people like want to write things down or something. Don't worry about it. Just go get them later. So, and then nobody ever pays attention at the beginning. So at the end, I'll give you the URL again if you really want them. Okay, and then the quick note, like the disclaimer stuff before we start talking here. So with some of this information, some of the work was sponsored by DARPA, and that's basically just some stuff at the end. And then whenever that information or that material comes up, I have to say that this does not necessarily represent the view or opinion of the U.S. government or any agency of the U.S. government. And then on that note, neither Iowa State. This is my own opinions about things, and it should be construed as such. So about me, I've been a student for kind of a long time. I worked for the university the last 3 years, and as of the 15th this month, I am now a PhD candidate. So working on my PhD and hopefully finishing that sometime soon. And I've worked some places, and I guess the last 2 or 3 years we're working on these 2 big DARPA grants. Each one was about $5 million grant for the university, and so that's kind of where a lot of this stuff is coming from. So let's just a little overview of the talk. I kind of want to establish a common understanding of side channel vulnerabilities, and to do that I'll provide a few examples of side channel vulnerabilities, and I'll kind of go in the order of like more physical to hardware to software, generally in that order. I'd like to discuss the causes of these side channels, and then more importantly, let's discuss how we can prevent those or at least detect them in software. And really what I want to do is get to the talking about software. Okay, so this is a very goofy little video, but it's going to kind of set the stage for what I'm going to talk about.
There's a hole in my bucket, dear Liza, there's a hole in my bucket, dear Liza, a hole.
Okay, so yeah, pretty goofy, right? Oh, YouTube. You can find anything on YouTube. So this is the theme. I don't know. I always have a theme for a talk. That happened to be the theme. So how big is Henry's bucket? And what information do we have to work with? What do you guys think?
How much fell out?
Yeah, so like how much water was falling out of the bucket, right? So there's a hole in the bucket, so it's information leakage. Get it? Okay, yeah.
What do you mean, no pun?
No pun, yeah, pun intended. So anyway, right? So if there's some sort of information leakage, you can infer something about the greater state of the program, or in this case, the bucket. How much water does the bucket hold? So anyway, what's a side channel? Well, historically, side channels were used to describe things like attacks to physical crypto hardware systems. So doing things like power analysis or looking at timing information, looking at, does the system give off some sort of acoustics? Does it have some sort of clicking, or something? Faults, and usually hardware faults, but electromagnetic radiation. So if the circuit kind of heats up during operations or gives off some light or infrared radiation. All those things we can use to kind of start piecing together what the circuit or the system or whatever it is we're trying to reverse engineer, what that's doing. So if you imagine you have some sort of like circuit that you just acquired, right, through some black ops operation or something, right? You have this enemy crypto system. So what are you going to do to start figuring out how it works? Well, you're just going to start kind of like feeding inputs into it, right? Start turning on and off things. And you start plugging these things in and looking at these things on the left, right? So this power analysis, how much power is the circuit taking? Is it giving off heat? And does it do it for certain inputs and not others? And eventually you kind of start to realize that some of these operations require more amounts of things than others. And you can start to kind of like piece together, oh, maybe this circuit's just, it's just an add operation, right? And you start to kind of pull apart the circuit and figure out how it's working. So this is just an adder circuit, but that's generally how you're going to approach the problem because you don't have much other information to work with. So here's kind of a fun example of a side channel. So DARPA in, I think it was like 2010, had this paper shredder challenge, and it was $50,000 as an open competition, and the prize would go to whoever could unscramble 5 of these shredded documents first. So this went on for like a year or two, but the puzzles, all 5 puzzles, were eventually solved by one team named All Your Shreds Belong to US. And so this is a picture of their solution they submitted. And you can see it's pretty well shredded up there, tiny little pieces. And so a little of life's irony, there was about 9,000 teams competed. One team that All Your Shreds Belong to Us solved all 5 puzzles. And the way they did it was by using these hidden printer dots that were added by the printer manufacturers and the US Secret Service. And the little printer dots, it's really hard to see there, but here's a black and white version of it. These little printer dots get added, and the manufacturers add this logic into your printers to print these little kind of random dots, but in a certain way so you can figure out what printer it was. Because the US Secret Service's mandate is to detect counterfeit currency, right? So if we can kind of add like a little print underneath the, in all of the documents that get printed, we can trace back, okay, it was this printer, and maybe these people bought these printers, and we can figure out that sort of stuff. But the team that used this basically just scanned in all the pieces of the shredded document and then used these printed dots as kind of a reference grid to identify the fragments of the document, right? Because not the dots won't be too close together. You can kind of reorganize them that way. So pro tip, burn your documents if you really want something gone, right? So the shredders, there are ways to get them back. Okay, so here's another one. I really like this story. So this kind of fake German writing basically says, like, attention, keep your cotton picking hands off this mess, so just relax and watch the blinking lights, right? And this is kind of a thing that's kind of floated around for a while, so those are the blinking lights, right? And what are the blinking lights, right? Why does, if you go in your server room, why are there blinking lights on everything?
Transmit, receive.
Yeah, transmit, receive, right? So yeah, historically we had lots of blinky lights on all sorts of things, right? And it would kind of indicate some state of the system, but as the computers become faster and more reliable, we started either just removing those lights or we kind of left them as like diagnostic indicators. And in networking gear hardware, specifically, everyone really liked the blinking lights because you go into the server room and if they're just like not blinking at all, well, they're probably, you're not getting any packets, right? No packets. But if it's just going crazy, it's like, Christmas in there, then, you probably have a packet storm brewing, right? So it's kind of a nice just visual indicator, and we really like our blinking lights, right? But there's a problem with this. Couple problems, actually. So one, LEDs have a very fast on and off time. In fact, it's almost instant, and that's why we use them for things like controlling fiber optic cables, right? It's very fast transmit and receive, turning a light on and off. It's not like an incandescent where there's kind of like a warm up and a cool off period. And these LEDs were wired directly into a serial data line, right? So basically what that means is each blink on your device was a 1 on the wire in your network, right? So if the LED is off, that's a 0. So this is definitely way too fast for a human eye, right? We have lots of traffic flying around the network, but it's not too fast for a circuit and a telephoto lens, right? So what you can do is you can actually build a very simple little circuit, hook it up to a nice little telescope, aim it at someone's switch, right, and then actually decode the information on the wire. So you can hook this up to like Wireshark or something, right? And so some researchers did this in 2002, and it was kind of a surprise to everyone that it's kind of obvious, but it's pretty easy to decode this stuff. So the solution is to just put duct tape over the LEDs, but we still want our blinking lights, right? We kind of like those; they're nostalgic to us. So now is kind of the arms race. So we're trying to figure out, how do I give you blinking lights without revealing something about my network, right? So the first solution, this was the solution recommended by the authors, was to do something called pulse stretching. So if you see a 1 on the network, you just leave it as a 1 for a certain number of clock cycles. So in this case, it's a 3x, right? So 3x pulse stretching. But so here's an example of even with 5x, we can actually recover this information because we know that even with pulse stretching, there's a certain pattern to it, right? And we can figure out, we can actually recover, even with 5x pulse stretching, we can recover 99% of those bits. And packets have error correction codes, so that's nice. So we can just brute force and guess the rest of the missing bits. The better approach is to just very low frequency sample. So you don't wire it directly into the serial line. You just sample every now and then, and that kind of gives you a representative sample of what's happening on your network without revealing all the information. So the origins of side channels, I kind of want to talk about where these come from, and in my opinion, I mean, you can kind of boil it down to this short story, is that we want to optimize things, right? We want to reduce the cost of things, the amount of power things take, the amount of heat things give off, and we want to increase their speed and efficiency, right? And so if we consider synchronous versus asynchronous digital logic circuits, synchronous circuits kind of like the digital logic course you probably take as like an undergraduate in a comp sci or like computer engineering degree. So a synchronous circuit has a clock, and it just kind of is like a drum. It's beat, 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 and all the operations happen on that beat, right? So we have a fixed clock, and all of the operations take the same time. So if you're doing like an adder circuit or something, your best case and your worst case are the same, right? Which means every case is the worst case, right? So we want to improve this. So kind of the hot new research topic was building these asynchronous digital circuits. So we don't have a clock. All these little modules of logic kind of operate independent of each other, and when they finish, they kind of communicate to each other and pass on the work, and when they're done, they're done. So now instead of having every case being the same type of case, you have best case, worst case, average case, right? And the idea is that the average case costs less than the worst case. But now all of a sudden we have this kind of asymmetry, right? We have this ability to differentiate between operations. So if we go back to like our, let's see, all the way back to this guy. So if you think about an adder circuit, right, some of these operations are taking more time because when you add up these numbers, so a 1 and a 0 is a 1, no extra work there. A 1 and a 1, we now have to carry the 1. That's a little extra time, right, a little extra power to do the operation. So then we get a 1 and a 1, we have to carry the 1 again, right? It's a little more extra power. And so that will take a little extra time. And if we have the ability to kind of differentiate that, then we have a side channel. Okay. Okay, so in software, we have side channels leaking primarily through timing information. And these are really scary because time kind of just happens everywhere. You don't have to be on the system, right? You can be a remote attacker when you attack something through timing information. And then memory space usage. So this is kind of the content, the order of memory, the size of memory. So really, what is your output? If it's writing to a file, maybe it's the order of things that you write to the file, or how much memory you take up in the program. So here's just kind of on the bottom right, there's just kind of a simple snippet of code, right? We have some if condition, and if it's a secret, we do something that takes a short amount of time. If it's not a secret, we do a long amount of time, right? And these are kind of the root causes in software of where these differences come from. Okay, and these are related problems, and I can get into that more later. But these optimizations are everywhere. So one, we just do it directly in our software algorithms, right? All the branches, if we short circuit some logic and a conditional, any loops, all have conditions in them. Our compilers do tons of this for us. Every time in your architecture, if you go to RAM versus going to disk versus, all the different level caches in the CPU, all of these take different amounts of time. So in software, this relates to reading from an array. So anytime you write something to memory, you're introducing timing differences. Going down to like the operating system, you have your process scheduling and all the optimizations there. Going down to the CPU, you have branch prediction and so on. So these optimizations are just everywhere. You're not going to just like get rid of them. Okay, so here's another, we're moving closer towards, this is software now. So here's a fun attack you can do. So say we want to demask someone on the internet. So we want to demask a Google user. So let's select some Google users to target. So just figure out their email addresses. Then create a Google Drive document and invite those targets. Don't check the box to send the notification to them. Just leave that and go ahead and invite them to the document. And then you can use HTML and JavaScript, and you can create like a nice spear phishing website, like looks like their bank or their credit card statement or something, right? And since we can demask who these users are, we can make this site customize itself to like insert their name or their email or something like that, make it look like they're logged in, right? And the way we would do that is we can use create an image with the source pointing to the Google document. Obviously, a Google document's not an image, so when it fails, it will call the on air, right? But what happens is it takes longer to call the on air method because you have to go all the way to Google. Google has to do some validation and then come back. If it's not a user that you want, it goes to Google and says, I don't know who you're talking about, and then comes back, right? So Google has declined to fix this issue. It's kind of a very complicated fix. And I'm sure that people could find all sorts of these sort of things. So if you want, you can try this, and it should still work. So OpenSSL timing attack, here's a fun one. So just quick review of RSA. So RSA is the public-private key. And through our timing attack, we want to reveal the SSL's private key, right? So to decrypt something, you have a message M. And to decrypt it, you just take your ciphertext C times your decryption key, all modulus N, right? And only nobody should know your private key D, right? And then N is just the multiplication of two large primes, P and Q. So if you know the factorization of N, meaning you know P and Q separately, you don't know P times Q, because everyone knows P times Q. But if you know the factorization of N, then it's pretty easy to get back D. So this is just some work with the Chinese remainder theorem, but we can get back D pretty easy, right? So if we can figure out the factorization of N, we're golden. We have your private key, right? And so we can decrypt all your messages. Now, as the attacker, we can control C. We can ask, I want you to encrypt this, encrypt this, encrypt this. So we can ask lots of questions about that, right? Now, the issue is OpenSSL, the algorithm has the algorithm processing time is dependent on the ciphertext and the private key. And really, it's kind of two smaller bugs kind of built up to this. So there's an algorithm called the Montgomery reduction algorithm. And basically, it's a fast modulus operation. So they notice when OpenSSL makes notice that when C, your ciphertext, is close to a multiple of your Q and your private key, then if C is less than Q, it's going to be slower than the decryption of C is greater than Q, because in some cases we're going to use this Montgomery reduction. Right. In other cases, we'll just use the regular modulus, so it's slower. So there's a difference there, and there's also a difference in the multiplication routines. So when C is less than Q, they use this fast Karat-Cebu, I don't know how to say it, multiplication. Otherwise, they're going to use a slower multiplication because they noticed that when C is greater than Q, it's actually likely smaller because we're computing C mod Q, which don't worry about all the math. Just know that they're using two different routines in both of these, and it has these kind of greater than, less than relationships. And we're actually able to deduce N over the network, and I'll show you how in a second.
Specific to SHA versioning, or
I'm not sure the paper. I have the credits at the end for the paper, so I'm not sure exactly which things they're using. I know it was an RSA. This has been fixed since, but then there was a series of papers. One is called OpenSSL is still, or OpenSSL attacks are still practical. So it wasn't like fixed right away, but this is a couple years old now. So, but yeah, I'm not sure exactly which like hash settings or sub block sizes they were using. Okay, so we have this kind of greater than, less than relationship, right? And they have different timing differences. And we can control C, right? We want to know Q because then we can figure out this prime factorization. If we figure out one of these, then we can figure out the prime factorization. So what we can do is we can start asking repeated requests, right? We can keep feeding in different values for the ciphertext and looking at the timing difference and we can actually just do a binary search, right? Because we can see, oh, it takes a little shorter time, it gets a little longer time, a little shorter, a little longer, right? And we can kind of narrow in on the most significant bits of the private key. But once you get the most significant bits, here's this chart, the most significant bits control the value of the number. The least significant bits, it's just small changes in the number. Once you've gotten the most significant bits, it's hard to kind of tell the timing difference between a very small number. So you can guess, at least half of the private key. But then in order to finish the factorization, you just have to brute force it. But what's nice is you've guessed half of it already. It's now feasible to just brute force the rest of it. So this is kind of scary to me because it says even the side channel doesn't have to leak all of the information. It only has to leak a little bit of it. And then if you can just reduce the search space of the problem more, you've still won, right? And this is all exploitable over the network. Okay. And then another one here, I really like these underhanded C contests. In fact, the 2015 just opened up, so if you want to submit an underhanded C program, the kind of the background on the underhanded C contest is you have to write source code that in C that's capable of passing a peer review, so it has to look benign but is actually malicious. And the execution has to kind of appear to perform the task correctly, and they tell you what the task is. So in 2014, the task was to censor a region of a JPEG image with just a black box, but somehow have a leak or a side channel that that redacted information can be recovered. So here's just a snippet of the winning solution, and it doesn't look like much. It's really easy to scan over these lines in the solution, and all this is doing is it's just writing the magnitude or the depth of the red, green, and blue components for a pixel, just in order. So it's reading a pixel from the file, and then it's writing a pixel, reading a pixel, writing a pixel, right? And when we want to censor, we just write zeros because 000 for red, green, blue is just a black pixel. Now the file format that they're writing to is kind of flexible, and it lets you kind of write things in a goofy way. And the way that they're doing it here is they're writing it character by character. So if you meant to write something like this is a red, green, blue, then red, green, blue, red, green, blue, you actually would write it out. The implementation actually writes it out like this, right? But a correct implementation would write out like this. So the value for the red would be 0, value for blue or green would be 0, value for blue would be 0. But you can see the implementation is actually writing out for each character of the original file. So what's happening is you're kind of leaking something about the size of the value that used to be there. And if this is a black and white image, you can tell black is going to be a 3-digit number, and black is going to be a 1-digit number because it's 0. White is 255, so it's going to be a 3-digit number. So if this is a black and white image, you haven't blacked out, you haven't redacted anything because you can reconstruct that perfectly just by looking at the sizes of the digits in the file. If it's a color image, you get kind of a choppy black and white version of what used to be there. So anyway, this one was pretty sneaky and it won. And if you guys want to submit your own, this is a good year to do that. So, okay, so for mitigations, unfortunately, it's kind of really hard to make software run in fixed time because you need to consider all of the sensitive information in your program and then all of the paths you can take through that program. And every time you have an if in your software, that's 2 paths, right? If it was true and if it wasn't. And if you nest them, you can have more. If they're non-nested, you have 2 to the n. So it's actually exponential in the number of paths that you have in your program. And you also have to consider every write to memory, which is basically everything in the software. So it gets really muddled really quick. Some people have had the idea of injecting just random time delays and things, but that doesn't really do much good for you because if you just repeat the attack over time, statistics kind of just wins and you can start to discard the noise, right? Because eventually that time delay is that pattern is gonna stand out over repeated attacks. And so this goes back to the OpenSSL. They did it over a network, right, which has random network delays in the packets, and they're able to reduce that noise just by repeating the attack. Okay, so this is where the DARPA stuff comes in. So right now we're working on the DARPA STAC program, which is the space-time analysis. I forgot what it's called. Anyway, space-time algorithmic complexity program. And so our approach is we have a human in the loop, so we don't try to do it all automatically. And really what we're trying to do is we're trying to amplify the human's intelligence to understand a program, so improve program comprehension. And there's this kind of nice spectrum of program analysis techniques where one starts from just manually auditing and the other goes to like completely automatic and dynamic, where I'm running the program and I'm just feeding inputs and looking for errors on the output. And there's kind of, some things in between where you try to abstractly represent the state of the program, and so people do all sorts of goofy stuff. Our approach is kind of closer to like this static manual, right? So somewhere in here. Okay, and so the challenges for this particular program are we are analyzing Java bytecode, so these are binaries. We don't have the source code to them. Although analyzing Java bytecode is a bit easier than analyzing like C code or compiled C code, because you get a little more back with Java, but it's still pretty tough. We don't know what the secrets are, so we have to figure out what the secrets are. We have to be able to address loop complexity somehow, which is actually a very hard problem, saying if something terminates or not. In fact, it's been proven that you can't say if all programs terminate or not. And we have to be able to somehow deal with the large frameworks and libraries that everything runs on top of. So like for Android, there's 6 million lines of Java code, plus another 3 million lines of C code underneath. So it gets pretty big. And then these are actually mixed code environments, so things can run in Java, can also go into C and C++ and native code. Okay, so here's kind of a demonstration of how we're approaching the problem. And for part of this, the project, I made just kind of a demo application that kind of is representative of a lot of the challenges we have to deal with. So this is just a small JSP web application. In fact, the source is online if you guys want to play with it, and you can run burp against it just to see how it all works. There's not much to it. There's a login page. If you log in as an admin, you get this nice little form to create an account. Otherwise, it's just an empty page that says secure area if you're not an admin. And of course, if you don't have an account, you can't log in. So the vulnerability is that you can infer the existence of users through timing, right? So it takes more time to validate a user it takes more time to validate a valid username with an invalid password than it takes to validate an invalid user, right? So as long as the user's in the database, it takes more time to validate the password. And so the attacker doesn't need to know any passwords. The password's not really relevant here. He just has to guess the usernames, right? And so our approach is, again, static analysis. So we're trying to look for expensive things. So the first thing we do is we just take an approximation. We say, okay, loops are expensive, and let's say nested loops are even more expensive, right? So first we generate that, and we look for loops within loops. And so in this application, we get a nice little graph here. So each one of these is a method. And so you see hash calls this pbkdf2, which is a kind of a scheme for taking hashes in like a feedback loop. So it kind of improves resistance to brute force attacks, because now the attacker has to do more work. So it's increasing the computation by n, when n is how many times you go through that loop. Okay, so we're just going to say that these are expensive operations because they use loops. That's just our approximation. And the next thing is, okay, so where are these loops used in the program? So we can look at this call graph. A call graph just kind of says each method calls the method that it's connected to. So we see that there's two services here. And I guess I should know, I didn't write these methods. These methods get generated when you compile the application. So already things are getting more interesting just because it's compiled code. But there's two services that use this. One is the authenticate user, and one is the create user. So create user has to create the password hash to store it, and authenticate user has to hash the user's password and then check to see if it's right. So the next step is to say, okay, so it's definitely it's definitely expensive, but are either of these things, done in some sort of branch? Meaning, there could be a case where it's expensive in one case and a case where it's expensive in another case. And so what we do is we generate this thing we call an event flow graph. An event flow graph is basically a graph that shows us all of the conditions, but then tries to throw away as much information as it can that's not relevant to what you want to know. So in this case, there's a bunch of conditions removed because we can say, oh, each path, no matter if you go through this condition, you'll end up, at the bottom where what you're interested in. So this is actually much smaller, so it's a compacted graph, just because as humans we can't really deal with too much information. So anyway, we see that there's quite a few conditions here, but the first one here, this one highlighted in yellow, is the hash logic, and this is the first condition. So we just start kind of inspecting these conditions systematically, and if you click on this condition, it jumps to the result of an SQL query. So just remember that. The next step is we found that something happens conditionally that's expensive, but is it tied to some sort of secret? So what we can do is we can actually follow data forward in a program. So here the things in red, I know you can't read the graph, but the things in red are two secrets. One's the email and one's the password input from the HTTP request. And we just follow the data forward and see if it goes somewhere that we recognize. So in this case, we see that the data actually dead ends in the hash function or into an SQL query. So we can click on any of these graphs and it jumps to like the decompiled Java code that we have. So here's the decompiled Java code. And what's happening is we're saying select all rows from the database, or all columns from the database users where the email is the input email, and limit that to one result, right? So then this Boolean next iterates through all the results in the query. Oh, and I guess the email is set here by the setString method. And then if there's a next, meaning if there was a result, we go to the hash function. So this is our if condition. So we only hash the username, or we only hash the password if the username exists in the database, right? Okay, so we can actually go through this attack with burp, what we've done quite a few times in here, and I'll go ahead and play it here. So first things first, we're just going to kind of play with the web app and kind of get a feel for it. We're doing our reconnaissance, right? Where's my mouse? Okay, no mouse. I just have to wait. So anyway, we're going to go ahead and log in. So we log in as admin, and we can log out. Okay, cool. And so this is my attacker machine just running Kali. And I'm going to go ahead and load up the web page. So drop in the IP address. And this app was just running on port 8080. Okay, and then I'll also fire up Burp Suite. Okay, so once Burp Suite fires up, I'm going to go ahead and make a request because I want to get one request and capture it in Burp Suite. So if you remember with Burp Suite, you have to set the proxy up. So doing that real quick. Okay, so did we get anything? Okay, yeah, so we got a request. Oh, turn intercept off, yeah. Sorry guys, I was planning on skipping forward a little bit, but I can't even find my mouse, so we just gotta watch it. Okay, so I'm just gonna go ahead and log in. I'm logging in with Bob at example.com. Okay, Bob at bob.com. And I don't care what my password is, so I think I just entered Bob or just like smashed the keyboard or something, right? So it's invalid. We know the password doesn't work. You know, fat chance that would actually work. But it doesn't matter because I just wanted to capture the request so I can replay it. Okay, so I'm going to go ahead and send that to the intruder function of Burp Suite. And then what I'm going to do is I'm going to fiddle some things. I'm going to start fuzzing the application. Okay, so leave the session ID the same. That's fine. I just want to replay this, right? So The password, I don't care. I'm just making it test. I don't, it doesn't matter what it is. It's always going to be wrong. And then for the emails I'm going to test, I'm going to load in a test of emails. So I've got just a little set of emails that I want to know if they exist on the server or not. And I'm going to go ahead and run the attack. And so this is going to just fuzz all those emails. Okay, and now the content length is the same on all of them, but what's different is the response time. So you see the 3 emails on the bottom, all those users actually exist on the server. And the users on the top don't exist, right? Because it took a shorter amount of time to tell me that those users don't exist than the ones on the bottom, right? Okay, so is my user base really a secret? So some people would argue this, and I would say, well, it depends, right? If you're this website, it probably does matter a lot, right? And if you guys don't know, like this website just got hacked like last week or 2 weeks ago, and all their like user bases out there, and they said they deleted accounts, but actually they didn't. Yeah, so definitely going to be some interesting social fallouts from this, but I don't know. So it really depends on what your secrets are. If you don't care if someone knows who all your users are, then you don't care about this, right? So anyway, I guess the fix for this code, the easy fix is to just hash the password regardless, even if you know the user's not in the database, so you have the same time output, right? That's one way to fix it. Okay, so some predictions for the future. I think currently side channel exploits are kind of like this. You're vulnerable, you just don't know it yet, or you don't really care yet because you haven't been getting hit with it. But in the future, I think they'll be more like this. As we develop better tools to find them, the attackers will have access to those tools as well. So some homework or things to do. I would just kind of enumerate, what are all your kind of entry points in the application, so what are all your REST operations, and look at, if you can, do some profiling of the timing and at least the response. So there's some other good examples online where the ordering really comes into play. So like the order of your HTTP headers can actually reveal information. And a lot of the frameworks will do this because they weren't really paying attention to things, or they optimized for speed, but some of these things can reveal things. Or the order of your parameters. So there's one online where the get parameters were all the same, but the order of it would reveal something, whether the user was logged in or not, or something about a private library. Your cookies, error messages, just kind of looking at the ordering, the content of each of those. But really, just the advice would be start by thinking about all of your secrets, and then think about the attacker's operational budget, right? So earlier I said you can introduce these like random timing delays, but the attacker can still do it. It just makes him take more samples, right? So if you think about his operational budget, and that might have something to do with, you have rate limiting in place, or it'll send up a red flag if he requires him to do this many queries against your system to figure something else out. You can kind of think about it as like an economics game too. So in closing, if there's a hole in your bucket, dear Henry, then fix it.
Dear Henry, dear Henry, dear Henry, then mend it. Dear Henry, mend it.
I think her lips are off.
Yeah.
That's the scariest part.
So I got lots of references on here if you guys are interested. And there's lots of other cool presentations. I really liked this one by the first #1 there. It's a one on ShmooCon from this year that talks about side channels. And it's more aimed at like C, but it's pretty interesting. And yeah, right there at just at my website. So yeah. So if you guys have any questions, or if you want to talk, or just open it up for discussion, whatever.